All right, so welcome to discussion 1 video walkthrough. We're going to go ahead and start working on problem 1. Hopefully Vinay has gone over a good walkthrough of how matrix multiplication works, matrix vector multiplication works, because we're going to be using that directly in problem 1. So problem 1 says the square of a matrix is its product with itself, A times A. And the first thing we want to do is that we want to show that 5 multiplications are sufficient for computing the square of a 2 by 2 matrix. So I'm going to give you a minute. You should pause and see how to do this. Just start with a matrix that looks like A, B, C, D. Try to square it and convince yourself that this can be done using just 5 multiplications. Okay, so you should pause now. All right. I'm hoping that you've tried this out on your own. But once you have, we can just go ahead and multiply these two matrices. And we will get A times A plus BC, so A squared plus BC. Then we will get A times B plus B times D. Then we will get CA plus DC. And finally, we will get CB plus D squared. We can simplify this to get A squared plus BC. We take out B to get A plus D. Here we can take out C to get A plus D. And finally, we can get D squared plus BC. So this is actually just 5 multiplications. We can see that by, give me 1 second. Right, we can see that this is 1 multiplication, this is another, this is another, this is the 4th one, this is the 5th one. So the BC is actually already done. So this is a total of 5 multiplications, which is what problem 1 wanted us to do. 1A wanted us to do. So now that we have that, let's move directly on to problem 1B. What 1B is saying, it's asking you to find out what's wrong with the following algorithm. Use a divide and conquer approach, as in Strassen's algorithm, except that instead of getting 7 subproblems of size n over 2, we now get 5 subproblems of size n over 2, thanks to part A. So we want to compute the square of an n by n matrix, and this time this is the algorithm we want to use. And in part A, we showed that you can compute the square of a 2 by 2 matrix using just 5 multiplications. So this time, instead of getting 7, we just get 5, and then we do the same runtime analysis as Strassen, and this should work, right? So I'll give you a couple of minutes, again, pause and think about it. But to get you started, the way we're going to write the matrix in this problem is just take an n by n matrix and write it like this. So this is something that can be done if we have a large matrix. We can sort of, here A is a matrix. So you can pretend like that matrix is actually made up of 4 sub-matrices. They're called the block matrices. And you can combine them together to get this one big matrix. And the operations on this big matrix work exactly in the same way. So you can just pretend like they're integers or they're some real numbers, and you can multiply them just as you would do for numbers. So again, pause and think about why the algorithm in part B is not correct. There are actually 2 points that you need to hit. So if you hit one of them, don't stop, keep thinking. Pause. And we're back. Okay, so let's go ahead and multiply this just as we would. This is going to look like now A squared plus BC. Then we get AB plus BD. And we get this multiplied by this, so we get CA plus DC. And then we get CB plus D squared. So unlike in the previous part, there is a question. Why does this not work? First of all, this is not 5 multiplications. So unlike in the previous part where we were able to do things like we were able to write AB plus BD as B times A plus D, we cannot do that here. For matrices, multiplication does not commute. So AB is not the same as BA. So we cannot just swap AB to BA and then take out B from the left-hand side. This is not allowed. So this is one problem. First problem is that matrix multiplication does not commute. But there's one more problem. Okay, but there is also a second problem, which is that the recurrence relation that we're going for looks something like this, right? We want to start with an input of size n, and what we want to do is square matrix of size n cross n. And then we want to write this as 5t n over 2 plus some other work, right? Plus some combination work. But this itself, it's not right. Why is it not right? Because understand, t here stands for squaring a matrix of size n over n. So you can imagine as having a function that squares a matrix of size n over n, and it takes in a matrix of size n, right? What is this t? This t should be the same as the other t, right? It should be the same as this t. So technically, this should be square a matrix of size n over 2. But if we go back up and look at our multiplications, that doesn't make any sense because that is not what is happening. This one is squaring a matrix of size n over 2. That is true. N over 2 cross n over 2. Sorry. N over 2 cross n over 2. So this is fine. But this is not. So even if matrix multiplication did commute and we did have 5 multiplications, this doesn't make any sense because this is a problem of multiplying matrices. And the recurrence relation that we would get would be one of squaring matrices. So the two t's don't match, which means in some sense we have something like t of n equals 5r of n over 2, where r is multiplying matrices. So this recurrence relation doesn't make any sense. That's why this algorithm does not work. Okay, now that we had that, let's move on to part C. All right, now moving on to part C of this problem. Part C says, in fact, squaring matrices, so let's write it down. Squaring matrices is no easier than multiplying them. If you think about this statement intuitively, you might think that squaring a matrix should be an easier problem than multiplying two arbitrary matrices. So you might think that, computing a squared should be easier than computing b times c for some arbitrary b and c, right? Because these don't have any structure. I mean, b can be anything, c can be anything. So multiplying them should be harder than just computing the square. There must be some tricks that we can do to compute the square faster, right? But we can prove that that is not true. And what we're gonna essentially be doing is something called a reduction. This is something we're gonna spend a lot of time on towards the latter half of the class. So don't worry about the word reduction for now, but this notion of proving that a problem is as difficult as another problem is going to be formally studied when we study reductions. But for now, let's just try to prove that squaring matrices is no easier than multiplying them. So what do I mean by that? What I mean by that is, if I can square a matrix in some polynomial time, right? So in some n to the power c time, of course, the square matrix of size n cross n in O n to the power c, some polynomial time, then I can also compute the product of two n cross n matrices in O n to the power c time, right? So what we're saying is something roughly along the lines of, if you can square a matrix in 5 seconds, then you can also compute the product of two matrices in roughly 5 seconds. Again, this is in O notation, so some multiple of 5 seconds, right? Or in maximum 5 seconds. That is a strong statement because we are saying that we intuitively think that squaring should be easier, but that's not the case, because if I can square in this much time, then I can multiply in this much time. And now we need to prove this. So at this point, you should pause and think about how you could prove something like this. So again, this is your cue to pause. Please do it. Okay, now that you've thought about it, the way this would work is essentially we need to, the way we do these kind of problems is you imagine that you have a black box. This is a solver for the squaring problem. So essentially you have a black box that squares a given matrix. So it takes in an input, a n by n matrix, and returns the square of the n by n matrix. And on top of that, it takes O(n) to the power c time, right? Now what you need to do is you need to build a black box which multiplies two matrices. So it takes in a matrix A and a matrix B, and it returns A times B. Again, A is n cross n and B is n cross n. And you need to make this black box also run in O(n) to the power c time. So this is what you are given, and this black box is what you need to create. Okay, so if when you paused previously you could not come up with an answer, see if you can come up with an answer now. As a hint, this black box is allowed to use this black box somewhere in the middle. Okay, so try thinking about it. All right, now that you have given it another thought, let's move here and see what we can do. Right, so let's see what we need to do. We need to take in two matrices, A and B, and then we need to build this black box. Here, let's take these two matrices and create a single matrix that looks like this, 0A, B, 0, right? So these are matrices again. This is a matrix of size n by n. This is a matrix of size n by n. 0 means it is a matrix of size n by n filled with zeros, and similarly this. And this matrix has size 2n cross 2n, okay? Cool. Now let's go ahead and plug this single matrix into our squaring black box. If we do this, what will we get in the output? So let's compute what the output will be up here. 0A, B, 0 times 0A, B, 0 is going to be AB, 0, 0, BA. All right. So this thing is just going to output that. And then what I can do is I can just extract first quadrant, right? So I can essentially extract out this part, which depending on how you want to think about it, takes n over 2 time or takes constant time, doesn't really matter. And then I will return that. So let's zoom out and take a look at this big picture, right? So what's happening is, once again, A and B were sent in to this big black box. Big black box, right? This big black box, the first thing it did is it created a big matrix of size 2n cross 2n. Okay, cool. Then it plugged it in, used this as an input into this black box which we were given, right? Now the question is, how long did this take? So this took O(2n) to the power c time, which is nothing but O(n) to the power c, because 2 to the power c is some constant, which we can drop, right? All right, so this thing took some small amount of time, right? So let's say concatenation, even if it takes 2n time, that's fine. Then we can think about this black box. It takes O(n) to the power c time. Then of course, this output comes out of this black box, so that doesn't take any time. And then extracting, like I said, you can think about it as taking some squared time or some sort of constant time, right? It's best to think about Extracting just takes constant time, right? And then we get our answer. So this entire black box took O(n) to the power c time in total, because it's sort of n to the power c plus 2n, so n to the power c wins, right? What have we done? We took a black box that we were given, and we created this big black box. This big black box is nothing but what we had to create. And in doing so, we have now shown that squaring matrices is no easier than multiplying them, because if you can square in n to the power c time, then you can multiply in n to the power c time, is what we have shown. This concept is going to come up again and again and again in the latter half of the class, so it's good to familiarize yourself with it. And this is the general way of doing these kind of problems. You imagine you have a black box, and then you create another black box. Okay? So if you have questions, feel free to post on Piazza. All right, now let's move on to problem 2 of this worksheet. Problem 2 says that you're given an array A of length n, and that array contains all the integers from 0 to n except for 1, and it's not sorted, so it's in some random order. In this problem, we cannot access an entire integer A with a single operation. The elements of A are represented in binary, and the only operation we can use to access them is fetch the jth bit of I. So the only operation we can do is fetch jth bit of AI, right? Using only this operation to access A, give an algorithm that determines the missing integer by looking at only O of n bits. And one note here is that there are O n log n bits total in A. Why is that the case? An integer n has log n bits. And in this case, we just pretend like all the integers from 1 to n have log n bits, and there are n such integers. So in total, we have O n log n bits total in the array, right? So we only need to look at O n bits, which means we can't even look at the entire array. Yeah, so go ahead and think about how you could find out the missing integer. To give you a hint, this will need to be a divide and conquer approach. Okay, so take a minute, think about it. If you come up with something good, and then again, I'll give you a hint, and then you should pause again and think about it again. Okay, so go ahead and pause. Okay, so a hint is just look at the least significant bit. So just look at the bit on the right end of all of the numbers. So look at n bits there and see what you can do from that. You should be able to delete some numbers as soon as you look at the last bits. So again, take a minute and think about that, and then unpause this video. All right. So now let's go ahead and start thinking about what we can do. So we have some numbers. We're missing the last bit. Let's say we count it up. Okay, let's write down the numbers in binary first. So 0, 0, 0, 1. Right, so let's take a look at this. If we have an even number of numbers, then we have an equal number. Just let's look at the last bit, right? Don't look at any of the others. If we look at just the last one, then we have 4 ones and we have 4 zeros, right? If one of these were missing, it will create an imbalance, right? What would happen is we would end up with just 3 ones or something like that. So that's something we can think about. Now you might immediately ask, well, what if, we have an odd number of numbers? Okay, so let's go ahead and also think about that. So let's say that we didn't have an even number of numbers, but instead we had an odd number of numbers, right? So if we had something like this, well, then we have 5 ones and we have 4 zeros, right? So let's say that we have even n, right? If n is even, then there are two cases. Either ones is less than zeros, or zeros is less than ones. If ones is less than zeros, then I know that the missing number has a 1 in the significant bit, correct? So let's say that the missing number is little m, right? Say that we have even n, m is the missing number, right? Then m's LSB, least significant bit, is a 1 because we're missing a 1, right? And in this case, we have m's least significant bit is 0. Okay, so this is what we know so far. And now let's say that we have odd n, right? Two cases. Let's say that m's least significant bit was a 1. In that case, we have 1s equal to zeros. Okay? If this is the case, then we say that m's LSB is 1. And the second case is where we have zeros less than 1s, right? Because let's say that let's say that this number was missing. In that case, we would actually just have 3 zeros, so zeros would be less than 1s. If zeros is less than 1s, then m's least significant bit is 0. Great. Now that we have this, let me change colors here really quickly. Okay. Consider this and this. Both of these, regardless of whether we have odd n or even n, means that m's least significant bit is 0. Amazing. And if 1s is less than or equal to zeros, then m's least significant bit is 1. Okay, so we're on to something. Essentially, look at LSBs, create ones list. So create a list of all the numbers with 1s in the least significant bit. So for instance, this one, this one, this one, and so on. Essentially all the odd numbers. And create 2's list. Let's call it 1L and let's call it 2L. Okay? All right. If the length of 1L is what? Is less than or equal to the length of, sorry, not 2's list, my bad. There should be 0's list. There is no 2's list. There should be 0's list. If the length, again, let's scroll up. If the length of 1's list is less than or equal to the length of the 0's list, then m's LSB is 0. Okay? Else, if len of 0 list is less than len of 1 list, sorry, made another mistake. M's LSB here is 1, not 0, right? Because if it is equal, then m's LSB is 1. If 1's is less than 0's, then m's LSB is 1. Okay. Else, if len of 0 list is less than 1 list, which is this case and this case, both of which have the same condition, then m's LSB is 0. All right. So far, all we've managed to do is find m's least significant bit. How do we construct the rest of it? Well, there's something we can do, which is, let's say that we have all the odd numbers out, right? So let's say that let's separate this list into 2 and see what we can do, right? So I'm going to write 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1. Let's say, and we have one more, 1, 0, 0, 1. Okay, that's one list. And let me write the other list, which is 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, and 0, 1, 1, 0. Right? So these are the 4 numbers we have from here, and these are the numbers that we have from here. Now, one of these numbers will be missing. So let's say either one, doesn't matter. Let's just pick one, right? So let's say this one is missing. If this one is missing, at this point of this algorithm, we will know that m's LSB is 0. Okay, if we know m's LSB is 0, then what we can do is we can take all the numbers. So essentially what it tells us that m has to be one of these, correct? And what we can note down, sort of imagine you have a little notebook, and on the side you note down that m's least significant bit is 0, correct? So m is definitely not one of these numbers, right? So we can discard all of these numbers, okay? And that's how you get sort of half a subproblem, right? We can immediately discard all of these numbers because I know that m must be in one of these. But there's more, right? The other thing that we can do is we can just go ahead and chop out the least significant bit of these numbers. And what we'll be left with is 0, 0, 0. Again, I'm just going to write this one again. 0, 0, 1, 0, 1, 0, 0, 1, 1. Okay, so I want to be clear about what's happening. These are even numbers. There's a fact from 61C, which is if you chop off the leading 0 from the end, what that does is floor division by 2. Okay, imagine you have 30. If I chop off the last 0, it does division by 10, right? If you have 37, in which case it's fine. If I chop off the last digit, it does floor division, right? So same thing here, it does floor division by 2. What I will be left with, these are even numbers, 0, 2, 4, and 6. What I will be left with is 0, 1, 2, and 3. But again, this is the missing number, right? So this is the missing number. I have the exact same problem now, except in a smaller size. So earlier, okay, let's redo this. Okay, so essentially this large list had 0, 1, 2, 3, and so on. And this smaller list is now a smaller problem. It has 0, 1, 2, and 3, and 1 is missing, right? So the exact same argument that we made above here is going to hold for this smaller list. Remember, we didn't make any assumptions about n, right? If n was even, then this would happen. If n was odd, then this would happen. So let's look at the big picture here. There are a few things happening, right? First, we look at the least significant bit. And then we have these 4 cases, right? Based on the least significant bit, we wrote this pseudocode. Okay, so this pseudocode told us m's least significant bit. But there's more that we can do, right? After we know m's least significant bit, we know whether m came from the odd numbers, which are here, or whether m came from the even numbers. If m came from the odd numbers, then m must be one of these, right? If m came from the even numbers, then it must be one of these. So we can immediately ignore one of these 2 lists. So let's think about this. Let me erase this line, and let's fill in this pseudocode here. If len 1L is less than or equal to len 0L, then m's LSB is 1. What that means is, here, let me write in comment, m is an odd number. What this means is I don't care about this zeros list anymore. I can completely ignore it. Okay, good. So I know m's least significant bit is 1. The other thing I can do is I can take, so these are the numbers, right? Again, I'm sorry I crossed over them. Let's see if we can get them back. We can. So if we have these odd numbers, what I can do is I can just chop out all of these 1s, right? So remember, in the beginning, this was 1, 3, 5, 7, 9. I'm going to do floor division by 2 to get now the new numbers. This is 0, 1, 2, 3, and 4, right? And out of these, 1 is going to be missing. So essentially, if this was a function of all numbers in ARR, if this was a function that took in an array, and I'm just going to leave something blank, we'll see why. If this was a function that took in an array, here we can call this function again, right? Let's call this f. We can call this function again, but this time we can completely ignore the even numbers, so we can just call it with the 1s list, okay? And we should give it the information that, you know, m looks like x, 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 x here is unknown. So x, 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 and we know that it looks like the 1 at the end, right? So here we don't know what m is. So this is sort of m, and we're constructing it as we go, right? So m looks like this. We give it that information. Perfect. M's LSB is 1. All that means is prepend 1 to m. Prepend 1 to m. Yeah, so it says prepend 1 to m because basically, let's say that I'd already known that m is 0, 1, 0. Then at this spot, you need to put the 1 is what it says, right? And then we call f with 1's list and then whatever m we have so far. So here we'll say m, right? So m equals prepend m 1 to m and then send m back to it, okay? And we're missing something though. So which step did we miss out? A step that we missed out is we need to actually chop out those ones. Remember, this was actually one, this is what it looked like. I chopped out the least significant bit to make it the same problem as above, as the starting problem, right? So here we need to do chop LSB from 1's list, okay? I do that, I prepend 1 to m, and then I call this function again recursively. And that same thing you can do for else, which is m prepend 0 to m in this case, and then chop LSB from 0's list. I went over the example for 0's earlier, which was 0, 2, 4, 6. Then it becomes 1, 2, 3, and 4. Sorry, it becomes 0, 1, 2, 3, right? So it's the same problem, except one of the numbers is missing. And then this whole thing applies inductively. So chop LSB from 0's list, and then call f with 0's list, and then the m that you have so far. And that's it. This is the entire problem, right? Eventually, we will just have sort of nothing left in the array, at which point, that's fine. M will just come out of it. Once m has filled up all of its positions, then you can return m, right? And so this is the pseudocode. The main idea, I'm sure you can write in your own words now. And the proof of correctness essentially is an argument that involves this, right? So what you say is that, we consider all the cases. So of course we can chop out the bits because these two cases are the case when 1's is less than or equal to 0's. These two cases are when 0's is less than 1's. So we know the least significant bit of m. And once we know that, we can recursively build this up by chopping off the subproblem. And that's what the proof of correctness looks like. You can read a more formal version of it in the official solutions, but you should try writing it on your own first and see, and then compare what your solution looks like versus what the official solution looks like. So that's it for this problem, except one last step, which is now we need to argue about how many bits we looked at. So the number of bits that we looked at the very beginning, we had to look at all n bits because we had to look at the least significant bit of all of the n numbers. So we started with a problem with an array of size n, right? And then we called this, we called 1. So this is not 2, right? Because there's no 2 outside here. And the reason for that is because we call the same problem with an array of half the size, right? We either call it with 1's list or we call it with 0's list, not with both. Okay, plus the amount of work we did here is O of n. And the reason for that is because here we had to look at all of the n bits, all of the last bits, right? And so this comes out to be O of n bits. This says that we looked at O of n bits, which is what we wanted. But there's one more thing, which is we need to look at the runtime analysis of this. So the runtime analysis of this, instead of t, I'm going to use r this time, okay? It's just a different variable. So we started off with a problem of size n, right? And then again, our problem became half in size, so that part is fine. But now we need to carefully think about what goes in here. We did not do just n work, right? Creating these two lists actually take more than n work, because here, let's think about it. We need to create this 1's list, and we need to create this 2's lists, right? And into these, we need to copy over sort of the odd numbers and the even numbers, right? If we have to do this, then we have to be careful, because copying an odd number, this odd number, right? So this one right here, or any one really, is going to have log n bits. This is from the same argument before, right? Which is that the argument that I'm talking about is here, which is that an integer of size n, that integer n has log n bits. Same thing here. This odd number has O of log n bits, correct? And I need to copy it over into this auxiliary array one by one, bit by bit. So copying this takes log n time. Copying this takes log n time, log n, log n. And how many numbers am I copying over total? N. So copying over all numbers takes n log n time. Okay, so this is the important part. Over here is going to be n log n, and if you solve this, you will finally get O n log n. Now you might be wondering, how come we don't count this copying as looking at the bits? Because we're not really looking at them, right? We're just sort of copying at them. So remember, the question says that you are only allowed to access the bits by fetching the jth bit of AI, right? So when copying them, we are just sort of blindly copying them over, but the only analysis that we are doing is on the least significant bit, which is only on the last n bits, one from each of the numbers. So we looked at n bits, but we copied over n log n bits, which is what takes this n log n time. Which is what takes this n log n time. Okay. Again, if you have any questions, feel free to post on Piazza or on the YouTube channel, I guess. But yeah, feel free to ask any questions about this, and good luck.